is, you have this small little chirkut titled Spring Pulley Illustrations. First of all, I would give you a basic understanding of how to deal with it, and the method that I'm going to deploy is energy methods to solve these problems, right? So I will just discuss these problems, and that would enable some understanding on energy methods used to find. See, one way is the force method, where you discover, well, force proportional to displacement from the mean position and is restoring in character. You then conclude that the motion is simple harmonic. Or you write an energy expression. You write an energy expression, and for the oscillator, the energy remains preserved. So you say dE dx is 0. Once you say dE dx is 0 and you find acceleration turns out to be minus kx or minus kx plus c, or rather minus a positive constant into x or a minus positive constant into x plus c, then you can conclude that the motion must be simple harmonic, right? A equal to minus omega squared x plus c1 or A equal to minus omega squared, both represent simple harmonic motion. The only difference is the mean position is not the origin in both cases, right? Now so pulley spring illustrations. Problem number 1, which is about a system of this kind. There is a spring of force constant K passing over a pulley with a mass M attached to one end. Mass M attached to one end of the spring. Now we want to find the angular frequency of oscillation of this mass. First of all, we want to be sure that the mass will execute simple harmonic motion, right? Now, for sure, while this mass moves up and down under the connivance of gravity and spring forces together, right? What would happen is that at some instant, the spring will also come to its natural state. The spring will also arrive at its natural state. So there is, say this is x equal to 0, the unstretched length of the spring or the natural state of the spring. Right? Yes or no? Now, obviously the mass will descend under the influence of gravity. Mass will descend under the influence of gravity. It will gain velocity. Right? Now, after a while, the mass moves to this position. X units below the natural. This is not an equilibrium position though, because spring force is 0, but there is unbalanced gravitational force. So this is not equilibrium position. This is only x equal to 0, which is the natural state of the spring. After a while, the mass descends down by an amount x. Right? And by the time it descends, it would have gathered a velocity v. Yes or no? Now, let me write an expression for the total energy of the system. Let me go ahead and write an expression for the total energy of the system, right? And in this intermediate state, the total energy of the system in this intermediate state is, okay, first of all, suppose, see, there are two potential energies involved here. There is elastic potential energy of the spring, there is gravitational potential energy, right? So if this point is 0 of GPE, 0 gravitational potential energy, then above this will be positive gravitational potential energy, below this will be negative gravitational potential energy. How about it, right? So if this is 0 gravitational potential energy, do you realize this would be minus mgx? This is going to be minus mgx, right? then there is elastic potential energy of the spring. If this point has descended down by an amount x, the spring must have got elongated by an amount x. So there would be elastic potential energy half kx squared in the spring. Plus there is kinetic energy of the mass, which is half mv squared. This is the energy as a function of x, total energy of the system as a function of x. Now while the mass moves up and down, the elastic potential energy changes, the gravitational potential energy changes, the kinetic energy of the particle changes, but it's all moving in a conservative field, force field. Therefore the total energy will be independent of x. E must not depend on x. Although its constituents depend on x, E must be independent of x, must be the same for all x. How about it? Right? That means, can I not say that dE dx must be 0? If E does not depend on x, then rate of change of E with respect to x must be 0. So dE dx must be 0, right? So dE dx 0 would mean this is minus mg, this would be kx plus 2v dv dx, 2 will get cancelled. This must be 0. Hey, but v dv dx is acceleration, isn't it? V dv dx is acceleration. So now, in any case, v dv dx, which is the acceleration of the mass m, is minus k by m into x plus g. That's the acceleration. So acceleration is minus, this becomes, this constant therefore must be omega square for the oscillator plus some other constant. The equilibrium position would be, when you put this equal to 0, you get x equal to mg by k. That will be the equilibrium position for the oscillator. And a equal to minus a positive constant into x plus some other constant represents a simple harmonic oscillator with the coefficient of x without the minus sign representing the omega square. Right? So the omega, that this executes simple harmonic motion with omega squared equal to k by m or omega equal to root k by m. Yes or no? Right? This is also called the natural frequency of oscillation of m. I mean, if you release it, this is what it would do. It would execute simple harmonic motion with a natural frequency, angular frequency, root k by. Sometimes when I say frequency and omega, I almost consider synonymous. They only differ by a factor 2 pi. So take it the way you want to. Which part? This. See, a equal to minus a positive constant into x. What does that represent? Simple harmonic motion with equilibrium position being x equal to 0, position where a is 0, with omega squared being equal to c, isn't it? In contrast, if there is a particle executing a motion in which a varies as minus cx plus c naught, this is also simple harmonic. The only difference is that the equilibrium position is not x equal to 0. Equilibrium position is where a becomes 0. That will be c naught by c1 would be the equilibrium position. I mean, did I not tell you f equal to minus kx is a simple harmonic oscillator with equilibrium position being x equal to 0. F equal to minus kx plus c1 is also a simple harmonic oscillator with equilibrium position not being x equal to 0 but x equal to c1 by k. Same with acceleration, the way forces could vary. Same way accelerations could vary. Right? Did I share all this thought in the first class on SHM? Right? Are you still confused, Arani? Sure? So acceleration turns out to be cx plus c1. Then this must be omega squared. K by m must be omega squared. Clear? The coefficient of x will give you omega squared without the minus sign, always. Right? Now, look at this. Where this is a string, whereas this is a spring. Again, I'll deploy energy methods to find the omega of oscillation for m. Not only that, I'll also first establish that the motion is simple harmonic, and subsequently, if a turns out to be minus or positive constant into x plus some other positive constant, some other positive or negative constant, the motion is deemed simple harmonic. Okay. Now, first things first. If the pulley moves down by a certain amount L, imagine that the pulley, it's a movable pulley, it's moving up and down. Let's say if it descends by an amount L, then there would be a length L of the string freed from here, and there is going to be a length L of the string freed from here. Now this freed up, where will it go? It will result in the descent of M. M will therefore descend by 2L, yes or no? If the pulley descends by an amount L, M will descend by an amount 2L. What? Now, suppose this is the state of things where the spring is in its natural state. Right? Spring in its natural state. Imagine that the mass, this is 0 GPE of the mass. This is natural state of the spring, unstretched state, and this is 0 of gravitational potential energy of the mass, right? So, if the mass after a while descends by an amount x, it would have developed a downward velocity also by this time. It would have developed a downward velocity by this time, right? If the mass descends by an amount x, it would have developed a downward velocity. And the spring, the pulley then would have got down by an amount x by 2. Yes or no? So the pulley moves down by an amount x by 2. If the mass descends by an amount x, see, because the pulley descends exactly half of what the mass descends. So if the mass descends by an amount x, the pulley ought to be descending by an amount x by 2. What is the extent to which the spring will get elongated? X by 2. Right? The total energy then of the oscillator. Okay. First of all, minus mgx for the mass. Spring has got elongated by an amount x by 2. So half of k into x by 2 squared. Right? Kinetic energy, half mv squared. That's E. E must be independent of x. It must be the same for all x. And therefore, dE dx must be 0. If dE dx is 0, dE dx, as you can see, is minus mg plus kx by 4. X square will give me 2x, which will, that 2 will get cancelled, this 4 will stay. Then mv dv dx, all of this must be 0. So that gives me v dv dx as minus k by 4m into x, right? Minus k by 4m into x plus mg. So this is acceleration minus a positive constant into x plus some other constant. The motion must be plus g. The motion must be simple harmonic with k by 4m being the omega of the oscillator. Yes or no? Omega squared. So omega squared is k by 4m. Omega must be root k by 4m. The angular frequency of the oscillator. Root k by 4m. Clear? And the equilibrium position being, put this equal to 0. So x equal to 4mg by k will give you the equilibrium position. If you plug in this equal to 0, that's the point where a is 0 and therefore f is 0, and that's therefore an equilibrium position. Simple? If this pulley descends down by an amount x, then this part of the spring will increase by an amount x, this length of the spring will also increase by an amount x. That means this entire spring will increase by an amount 2x. The spring length will increase by an amount 2x. Yes or no? So if the pulley descends by an amount x, the spring will increase by an amount, spring length will increase by an amount 2x. Now if the pulley moves down by an amount x, what about the mass m? The mass m will also move down by an amount x. Yes or no? Because the pulley is in sync with the mass. So if this was the if this was the position of the mass where the spring was in its natural state, this is also the zero of gravitational potential energy. By the time the mass comes to this point, say it acquires a velocity v, right? Then in this state, suppose this is zero gravitational potential energy of the mass. What is the gravitational potential energy here? Minus mgx. The energy expression in an intermediate state. Right? What is the elastic potential energy in the spring? Half k into 2x squared, because the spring has got elongated by an amount 2x. What is the kinetic energy of the mass in this? Half mv squared. dE dx must be 0. Yes or no? Right? So this gives me v dv dx as minus 4k by m into x plus g. Motion is simple harmonic therefore, and 4k by m must be omega squared, right? Omega squared therefore must have been 4k by m. Omega must have been therefore root of 4k by m, right? I want to find the natural frequency of oscillation of this mass m. Okay, you know the amount by which these two pulleys descend is also the amount by which the mass descends anyways, right? Now suppose at any given instant of time L1 be the position of the center of this pulley, L1 be the center of position of this pulley, and L2 be the position of the center of these two pulleys, right? Now, no matter what, see, the spring length varies, but the string length will remain the same, isn't it? The string length will remain the same at all times. I want to find out a relationship between L1 and L2, because the change in L1 will represent extension of the spring, change in L2 will represent descent of the mass m. Therefore, a relationship that would connect L1 and L2 could be a useful relationship. Yes or no? Right? Now, look, this length is L2, this length is L2, so 2L2 plus this length is L2 minus L1, isn't it? L2 up to this point and L1 up to this point, so L2 minus L1 is this length, right? And this is also L2 minus L1, so twice L2 minus L1. That's a total string length except the wrapped up length. Wrapped up length anyways does not change, right? So this string length, will it vary with time? No, this will remain the same. So this is a constant, which means twice of 2L2 minus L1 is also a constant, right? If this is a constant, that means 2L2 minus L1 is a constant. That means change in this is 0. Change in this means what? Twice delta L2. Change in L2 is delta L2 minus change in L1, which is delta L1. That must be change in this constant, which is 0. So delta L1 must be twice delta L2. Yes or no? Delta L1 must be twice delta L2. Right? That means if this mass descends by an amount x, which is change in L2, which will be reflected by change in L2, then change in L1 would be twice x. Change in L1 will represent what? Extension of the spring. The spring will elongate by an amount 2x. Yes or no? And say this was the natural state of the spring. By the time the mass descends by an amount x, let's say the mass develops a velocity v. From the original state, its descent by an amount x would guarantee gravitational potential energy minus mgx when it descends by an amount x. The spring half k into 2x squared. Half mv squared, the mass would have developed a velocity by then, right? That's the energy expression for the system as a function of x. Clear? dE dx must be 0. That means minus mg plus 4kx plus mv dv dx. That must be 0. Differentiating with respect to x, or v dv dx is minus 4k by m into x plus g, which is the acceleration. This 4k by m therefore must be omega squared. Omega of the motion therefore is root 4k by m. How about it? Does it make sense to all of you? Now, essentially, there are two springs joined somewhere. What you need to do is, imagine at some instant of time, spring 1, the one with force constant K1, has elongated by an amount x1. Spring of force constant K2 has elongated by an amount x2. The total elongation in the spring is x1 plus x2. Yes or no? Now think of it independently. This pulley, movable pulley, these were this portion and this portion of the spring. If the spring descends by an amount x, then this portion, if the pulley descends by an amount x, then this length of the spring will increase by an amount x. This length of the spring will also increase by an amount x, isn't it? This length of the spring will increase by an amount x. This length of the spring will also increase by an amount x. That means the spring length in all, this total spring would have increased by an amount 2x. Right? I'll repeat, kya? Right? So if this descends by a certain amount, the spring length increases by twice the amount. That means if the spring length increases by a certain amount, this will descend by half the amount. This will descend by half the amount, which means in this case the spring length has increased by x1 plus x2. So the mass must have descended by an amount x1 plus x2 by 2. The mass must have done this. And by the time it descends, suppose this was 0 GPE, gravitational potential energy, the mass has developed a velocity v. This, say, is x. x1 plus x2 by 2 is xa. So everything in terms of x. Let's say I want to write everything in terms of x. So x1 plus x2 is 2x. Is 2x. So in this state, what's the gravitational potential energy of the mass? Minus mgx. What is the elastic potential energy in spring with force constant K1? x1 squared. It has elongated by an amount x1. The other spring is elongated by an amount x2. So half K1 x1 squared for the spring. For this spring, half K2 x2 squared. For the mass m, half mv squared. Now, I want to write x1 and x2 also in terms of x alone. I have one equation, x1 plus x2 is 2x, but I need another connection between x1 and x2 so that I could write x1 and x2 entirely in terms of x. See, this is one single, this is the same segment of two springs. That means the force is the same everywhere in the two springs. The force is the same everywhere in the two springs, which is like the tension in the spring or whatever you want to call it, the spring force. These are like two springs joined this way, so it will be the same force everywhere in the two springs. That means K1 x1, the force in this spring must be equal to K2 x2, the force in the other spring. Yes or no? K1 x1 must be equal to K2 x2. Right? Or I could have written x1 divided by 1 by k1 is x2 divided by 1 by k2. Each is equal to x1 plus x2. Sum of the numerators divided by sum of the denominators. You understand this? If two fractions are equal, then each will be equal to sum of numerators by sum of denominators. Why? No idea, no? If two fractions are equal, then each will be equal to sum of their numerators divided by sum of their denominators. In the sense, if a1 by b1 is a2 by b2 is an by bn, then I claim that each of these will be a1 plus a2 plus an by b1 plus b2 plus bn. You understand all of this? Huh? Or it will be square root of a1 squared plus a2 squared plus an squared by b1 squared plus b2 squared plus b. Or it will be the pth root of a1 to power p, a2 to power p, an to power p, etc. All of this you understand, right? Huh? Okay. If I plug the minus sign here, then there will be a minus sign there. I can play with this, right? Okay. But what is x1 plus x2? 2x. So this is 2x divided by 1 by k1 plus 1 by k2. So I can find x1 in terms of x and I can find x2 in terms of x. And I can plug in this x1 in terms of x, x2 in terms of x. The whole thing will come in terms of x alone, the expression for E, and then I can differentiate dE dx equal to 0, and like before we can obtain the omega for the motion. The total, then look at this as one single thing, then that will move down by 2x. I want to find the angular frequency of natural oscillation for this system, right? again, from this position, let's say, if this mass m has descended by an amount x, then this center of these two pulleys would have also moved down by an amount x, right? That means this part of the spring would have increased by an amount x, this part of the spring would have also increased by an amount x. That means this one spring has increased by an amount 2x, this spring would have also increased by an amount 2x. Yes or no? So if it moves down, let's say it would have acquired a velocity v. Let me write the energy expression. E minus mgx plus, for the two masses, for the two springs, 2 into half of k, each of the springs would have increased by an amount 2x, x on either side, this one and this one, x on either side. So 2x squared and then half mv squared. Yes or no? Differentiate this. dE dx must be 0 or minus mg plus 8kx plus mv dv dx. That must be 0. So you will eventually get 8k by m. 8k by m will be omega squared. Omega would be root 8k by m. All's good? Any confusion? Eh? Yeah. Think of from here to here as one single spring and from here to here as another spring. See, suppose this is all a state of the mass where both the springs are in their natural state. Both the springs are in their natural unelongated state. All right. Hey, if this spring, for example, this top spring, it elongates by an amount x. Then this pulley will descend by an amount x. It will leave me x units of free length on either side. This mass m will descend by an amount 2x. If this spring elongates by an amount x2, this mass will descend by an amount x2. Yes or no? So, say spring K1 elongates by an amount x1 up to a certain point. Spring K2 elongates by an amount x2. Then the descent of the mass x is given by x2 plus 2x1. Right, very good. x2 plus 2x1. Yes or no? By this time, the mass would have acquired a velocity v. Now, let me write down the energy expression here. Let me write down the energy expression in this state. Minus mgx for this mass. Spring 1. Half k1 x1 squared, spring 2, half k2 x2 squared. Yes or no? See, independently, if this increases by an amount x2, then the mass will descend by an amount x2, contribution of this. If this pulley then goes down in the meantime by an amount x1, then this would have increased by an amount x1, leaving me another x1 and x1 units free on either side, isn't it? If this pulley descends by an amount x1, then there is x1 units freed up on this side, x1 units freed on the other side, which will result in an additional descent 2x1 of the mass. No? Plus half mv squared. I need to write everything in terms of x. I need to write everything in terms of x. x1 and x2, therefore, I need in terms of x. And then I'll say dE dx equal to 0 and perform the last rites. Very simple. Look, let me look at the free body diagram of this pulley. When this spring has elongated by an amount x1, this spring has elongated by an amount x2. Then there is on this k1 x1, there is k2 x2 and k2 x2 on either side. The pulley is practically massless. So k1 x1 must be equal to 2 k2 x2. Yes or no? The active string on both sides, will it not exert a force Tt on both sides, right? So can I not say k1 x1 must be 2 k2 x2? And x2 plus 2x1 is x, so I can solve for x1 and x2 in terms of x, and I can plug into this equation, into this expression. So E would be known entirely in terms of x, and then I can go ahead and say dE dx equal to 0 and obtain the value of omega as the coefficient of x, square root of that. Clear?